Hello, my name is Dr. Hena Asil, and I will be launching this year an online course in chemistry. It will include courses in O-Level, Cambridge, O-Level Edexcel, and International IAS Edexcel Chemistry. And I would like to present this as a free preview of what you would expect in the course this year. You will have 2 lessons per week, 1 lesson explaining a certain chapter, so I've divided the syllabus into several chapters, and the second lesson would be a discussion of questions and answers, which you would have downloaded in PDF form from the website drhenaasil.com. So you'll be provided with notes in PDF that you can download, which you can use in conjunction with the recorded lessons, and then you will have an assignment doing the questions that you download in PDF form from the website. The lesson after that, we will discuss the questions, whether your answers were right or wrong, and the correct answers that you're supposed to provide. So for this preview, I have chosen a chapter. We will be talking today about mass spectrometry. This is a chapter that you're supposed to know for the International IAS Edexcel. Okay, mass spectrometry is a method of analysis of samples in order to determine certain aspects about the sample. It involves an instrument called the mass spectrometer, and we can use it either to analyze a compound or an element. If we're analyzing a compound, then what we're trying to get is the molecular mass of the compound and the mass of its fragments. And this helps you to determine its structure, and we'll explain this in detail. If we're analyzing an element, then what the spectrum will show us is the mass of each isotope and the relative abundance of this isotope, so that we can use it to determine the relative molecular mass of the element. So, the mass spectrometer is an instrument that contains an electron gun, an electric field, a magnet, and a recorder. And what we do is we introduce the vaporized sample into the instrument. Once we have introduced the sample, it is bombarded by electrons from an electron gun. This causes ionization of the sample. Ionization means removal of an electron from the sample so that it changes into positive ions. So the first step in this analysis is the sample, which is a vaporized sample, is hit or bombarded by electrons, high energy electrons. This removes electrons from the sample and forms positive ions. Now the positive ions go through an electric field, and what happens in the electric field is that they are accelerated by the electric field. So the next step is acceleration of the ions. The positive ions are passed through positively charged electrodes, which generate an electric field, and this causes acceleration of the ions. So the ions move faster. Then they go into a magnet. So this magnetic field causes deflection of the ions. So the ions change their path. So the next thing that happens is deflection. And the deflection happens when the ions pass through the magnet, so that lighter ions are deflected more than heavier ones. So the sample is then separated into fragments, and the next thing is detection of the ions. This happens when the ions hit a detector that is connected to a computer, and this results in a spectrum being formed. Are we following so far? So what's happening in the mass spectrum? In the mass spectrometer, the vaporized sample is hit by high energy electrons. This changes it into positive ions. This is because when it is hit by electrons, it loses electrons from its atoms, and the atoms become positive ions. Now it then passes through an electric field. This causes acceleration of the positive ions. It then passes through a magnet, and this causes deflection of the positive ions so that the lighter ions are deflected more than the heavier ones. Now, once these separated ions hit the detector, then this results in a spectrum. A spectrum would look like this. So, for example, if we're doing the mass spectrometry of pentane, do you remember what's pentane? Pentane is an alkane. Alkane means it has only single bonds between the carbons. This pentane has 5 carbons and how many hydrogens? 12 hydrogens. So this is an example of a compound that gives a mass spectrum. Now, this mass spectrum of this compound is as is shown. The mass spectrum is actually a graph showing relative abundance of peaks and the m over e for each peak. Now, m over e or m over z, it's sometimes written m over e and sometimes m over z. It is actually the mass of the fragment divided by the charge. Now, if the charge is +1, that means that the m over e is actually the molecular mass of that fragment. So, we have a peak at what? The peak with the highest m over e is 72. This peak with the highest m over e is the peak that shows the molecular mass of this compound. Do you remember how to calculate molecular mass? So if we have pentane, pentane is something that has C5H12. How do we calculate molecular mass? Each carbon has a mass of 12, so we have 12 times 5, and each hydrogen has a mass of 1, so 12 times 1. The total molecular mass of pentane is 72, and that is the peak with the highest molecular mass or the highest m over e in the spectrum. So when we look at a spectrum and he says what is the molecular mass? Well, the molecular mass is the peak with the highest m over e. Okay, what about these other peaks that we can see? These other peaks are due to fragmentation of the molecule. Fragmentation means the molecule breaks up. It breaks up into many pieces. So, for example, if this pentane breaks up so that that last CH3 is removed, then the molecular mass of the remaining fragment is 57, and we do have a peak at 57. What if we break it further so that we remove that last CH2? Well, that is a molecular mass of 43, and we do have a peak at 43. Now, the peak at 43 is 100% abundance. The peak with the highest abundance is called the base peak. This just says that most of the fragments have a molecular mass of 43. So it doesn't really mean anything if this is the base peak, but it just means that many of the fragments have a mass of 43. What about the other peaks? Well, if I remove another CH2, I get a molecular mass of 29, so I do have a peak at 29, and the other peaks are also due to different fragments. So, looking at the molecular mass of the compound, the molecular mass of the compound is the peak with the highest m over e. The other peaks that show the fragments help to indicate the structure. So if we don't know what the structure of the compound is, we can determine its structure from the different peaks that it shows. Okay, let's try another one. Ethanol, for example. How do we draw ethanol? Ethanol is CH3, CH2OH. You remember that? Ethanol is something that has 2 carbons and an OH. So the positive ion of ethanol has a molecular mass of 46. And that is shown in the mass spectrum of ethanol. So the peak with the highest m over e is 46. That's because the molecular mass of ethanol is 46. Now, what about the other peaks? These are due to fragments. So let us take a look at what type of fragment. If I remove that last hydrogen, I should have a molecular mass of 45. Well, I do have a peak at 45. What else can I remove? I can remove that last CH3 from the other side of the molecule. So I end up with a molecular mass of 31. I have a peak at 31. What else can we do? Remove the OH so that I'm left with only the CH3, CH2. Then I have a peak at 29. Do we understand this? This last one, we just removed one of the hydrogens from the fragment that has a mass of 29, so I end up with a peak at 28. Are we okay with all of this? I hope I haven't confused you too much. Okay, let's take a look at some questions. This is one of the questions that you may have. He says a sample of bromine contained equal amounts of two isotopes, and the two isotopes are bromine 79 and bromine 81. He says complete the mass spectrum to show the peaks you would expect for Br2. Now Br2 means I have two atoms of bromine, but these two atoms could either be both 79 or both 81, or one of them 79 and the other 81, but then it could be either the first one 79 and the other 81, or the first one 81 and the other 79. So these are the four different options that we could have. That means if I have that first one where both bromines are 79, that means I should have a peak at 158. If I have both with molecular mass 81, then I should have a peak at 162. What about the peak at 160? The peak at 160 is when I have one of them 79 and the other 81. But then out of four choices, two of them show one with 79 and the other 81, and that means that the peak for 160 should be about twice the height of the peaks at 158 and 162. Do we understand this? Okay, let's try another question. A compound which has major peaks with mass over charge at a ratio at 29, 57, and 58 in the mass spectrum could be which of these? So you want one of these that you can break up and get a part that gives you a molecular mass of 58, another part that gives you molecular mass of 57, and another part that gives you molecular mass of 29. So let us look at the first choice that we have, propanal. Do you know what propanal looks like? Propanal has C double bond O, and then the H is attached to the C. If we calculate the molecular mass of propanal, it is 58. So that would give me a peak at 58, right? What if I remove the hydrogen that is with the CHO? Then I can have a peak at 57. What if I remove the CO, the carbonyl in the aldehyde? Then I will have a fragment with molecular mass 29. That means this should be my answer. Let's check the others just to make sure. So propanone is a ketone. A ketone has C double bond O and then a CH3 from one end and a CH3 from the other. If I calculate its molecular mass, it is 58. So it should give me a peak at 58. Mesh, that's okay. Now, the one where I remove one hydrogen would give me 57. That's correct. But then there is no way that you're going to get a fraction at 29. So this cannot be my answer. The other one, propane 1-ol. Propane 1-ol is an alcohol. Its molecular mass is 60. If I remove one of the hydrogens, it's 59. If I remove the OH, it's 43. If I keep going, it could give me a fragment of 29, but there is no way that it's going to give me a fragment 57 or 58. Do we understand what's going on? Propane 2-ol. Molecular mass is 60. It has, if you remove a hydrogen, it's 59. There is no way it's going to give you 58 or 57. Okay, and the OH is 43. So my answer is A. Do we understand why the answer is A? Okay, let's try another one. A mass spectrometer was used to analyze a sample of oxygen gas in which the most abundant isotope was O16. The oxygen was ionized and the ions were accelerated by an electric field. Suggest the formula of two different ions containing only O16 isotope. Now he's talking about oxygen. Oxygen is O2. And he's saying both of them are 16, mass number 16, not any other isotope. So if I pass it through the mass spectrometer, what kind of fragments can I have? Okay, either I have one oxygen, so the O2 divided into oxygens, one oxygen, or two oxygens together. And each of them, one oxygen, can either have a charge of 1 or a charge of 2+. The O2 can either have a charge of 1 or a charge of 2+. So he wants any two of these options. Now, the other question says, which part of the mass spectrometer separates ions of different mass? Do you remember this? Which part of the spectrometer separates ions of different mass? Where do we have the ions separating? Remember, it's in the magnetic field. When the ions pass through the magnet, we said that the lighter ions will be deflected more than the heavier ions. So this is where they're separated, in the magnet or the magnetic field. Okay, now for the two ions that we have chosen, remember we're supposed to have chosen two of these. For the two ions you have chosen, sketch their paths in the mass spectrometer after leaving the electric field and as they approach the detector. Remember, if they have left the electric field and they're going to the detector, that means they have passed through what? They have passed through the magnet and they are deflected. How are they deflected? Remember that whichever ions you choose, the one with lighter m/e will be deflected more than the one with heavier m/e. For example, if I have something with higher charge, like oxygen 2+, then the m/e is low. m/e is low, that means it will be deflected more. If it has less charge or it has more atoms, then the m/e is heavier. So it will be deflected to a lesser extent. Do we understand this? The one with higher m/e will not be deflected very much. The one with lower m/e will be deflected a lot. Okay? Following so far? Okay, let's try another question. Methanol and ethanol are both GLVs, which he says means green leaf volatiles. Now, if you see something like this in a question, just ignore, not ignore it, but don't stop at it. Don't say, oh, what does this mean? And things like that. If you don't know what it means, that's okay. Just move on. What is he asking? There are a number of fragment peaks which appear in the mass spectra of both compounds, but somewhat surprisingly, the OH+ peak at m/e17 is not one of them. So he's saying we have methanol and ethanol, and we have fragment peaks, but the one for OH+ is not one of them, so we don't have a peak at m/e17. Now, what is he asking? Suggest the formula and m/e values of two fragment ions that you would expect to occur in both the spectrum for methanol and the one for ethanol. First of all, do we know the structure of methanol and ethanol? You should realize that methanol is something that has one carbon and OHs, and the other has two carbons and OH. So these are the structures of methanol and ethanol. Now, which fragment would you expect to be present in both? Okay, so one fragment would be the one where I remove one of the hydrogens and I end up with a CH2OH fragment. This would be present both in methanol and in ethanol. So this is one fragment present in both. And the m/e for that is 31. Now, what other fragment do I expect to find? The one where I have the CH3 by removal of the OH. So I remove the OH and I'm left with the CH3 fragment. So this is something that will also be present in both of them. Okay? Now he's saying give the formula of one fragment ion that you would expect to be present in the mass spectrum of ethanol, but not that of methanol. Remember the structures? This is, the first one is methanol with 1 carbon. The other one is ethanol with 2 carbons. Now, which fragment ion would you expect to be present in ethanol but not methanol? Of course, the fragment where you have 2 carbons, because there is no way that the methanol will give you 2 carbons. So this is the fragment ion that you would expect. Are we okay with this? Okay. The next type of mass spectrum that we would get is if we're dealing with elements. And we said if we're dealing with elements, then we're trying to detect the relative abundance of its isotopes. Do you remember what are isotopes? Isotopes are atoms of the same element having the same number of protons but different number of neutrons. So they will have different mass number. So for example, when I do the mass spectrum for chlorine, we get a mass spectrum that has 2 peaks. Now, when I have 2 peaks, what this indicates is that there are 2 isotopes for chlorine. One of them has a mass of 35 and the other has a mass of 37. The one that has a mass of 35 has a relative abundance of 75%. That means that 75% of the atoms have a mass of 35. Now, the ones that have a mass of 37 are 25% abundance. That means only 25% of my atoms have a mass number of 37. So, this can be used to determine the relative atomic mass of the element. So, a mass number of 35 times the abundance plus the mass number of 37 times the abundance gives an overall atomic mass of chlorine of 35.5. So this is a question. Usually he will give you information about the relative abundances of each isotope, and he will ask you to calculate the relative atomic mass of the atoms. Again, the relative atomic mass would just be the mass of the isotope times its abundance plus the other mass times its abundance, and so on. And of course, that's divided by 100. Now, notice that for many of these questions, he asks you to give the answer to a specific number of decimal places or a specific number of significant figures. So please follow his instructions. If he says your answer should be to 3 decimal places, then your answer should be to 3 decimal places. Okay? Another question, again, he gives me a percent abundance and he says calculate the relative atomic mass. In the same way, in this case, he's asking for 3 significant figures. So this would be 55.9. Now, if we say that a substance X has a mass of 55.9, can you determine which element we're talking about? If you look at the periodic table, the element that we're talking about here, he's talking about isotopes of X, then X must be iron, because iron is the element that has a relative atomic mass of 56. So this question is related to the previous one. He's saying he got, in the spectrum for X, he got a peak at m/e 28. Now, if we know that X is iron, how can he get a peak at 28? Remember that the peak is the mass over the charge. I know that the molecular mass of X is 56, and that means if I have Fe2+, that means I have a charge of 2, then the 56 divided by 2 is 28. So the peak at 28 must be due to the fragment with 2 positive charges. Do we understand that? If he's asking for a molecular mass m/e for an element that is half of the atomic mass of that element, that just means that he is working with a fragment that has 2 positive charges. This is a general question. Explain why the 3 isotopes of X have same chemical properties. You should remember that isotopes of an element have same chemical properties because they have the same number of electrons in outer shell. Okay, so this was mass spectrometry, and that's how we use it in our syllabus. But then there are other uses of mass spectrometry in our everyday life. So they use mass spectrometry, for example, for radioactive dating to determine the age of fossils or the age of human remains. They can use it to determine analyze substances that they obtain from space. The most general use is for drug testing in sports. Remember that in sports they prohibit the use of steroids, but some athletes use steroids in order to enhance their athletic capabilities, make them stronger, faster, and so on. And that is prohibited in sports. So in order to determine if this athlete took steroids or not, we can analyze his urine for anabolic steroids, or his blood for anabolic steroids. We can also use it to identify the breakdown products from drugs in the body. So this helps to determine whether drugs are safe to use or they break down into dangerous substances in the body. We use them for quality control in general in pharmaceutical industry to control the use of drugs and their effects. Remember that the word drugs here applies to any medicine that is used by a person. Identify molecules from samples with potential biological activity. So it is used in many fields in our everyday life. Okay. If you feel that this course is useful to you and that you'll be able to follow it and use it to get a star in your course, I would be happy to have you enroll in my course. Go to my website drhanaaswil.com and enroll in the course, and I hope that it will be useful to you and help you to get a star, hopefully, as we go along all year. By the end of the year, almost all my students get stars in chemistry, so I hope you will be one of them. Thank you for taking the time to listen to this. Thank you.